Hello. Welcome back. I have just about an hour before I'm supposed to be in a meeting. I have biscuit. And thought I'd turn on the camera, do a little bit of work. You know, normal things. Normal person. Someday someone's gonna link me like a guide of how to talk to a camera, and I'm gonna be like, no, I don't want to do any of these things. I want to keep doing these weird kind of rambling half intros forever. My first task today is one of my students has asked me how this equation is derived. I'm going to be honest. It's been years since I studied this. I'm not sure I remember how any of it's been derived. But I'm going to try and work it out. Turn on. Connect. It's probably not a good idea, but a version of Bluetooth where you actually just have to touch the two objects together and they connect, I would use that. I fixed it. So it's honestly been a while since I thought about this, so it might be hard. Hey Lewis, how you doing? My first task of the day is to work out on behalf of a student where this equation came from. So I'm going to hang out for an hour or so, then I've got a meeting. Yeah, doing well. We just made a little office this morning for M upstairs, and I'm really pleased with it. It's like a nice, because I've got this nice space to work in here, and I feel really bad for having a nice space. Also, at this very moment, I feel bad for having a complete mop of hair, but there's nothing I can do about that. That is my life. So making a place for her up here that's a nice place to be is good news. Let's try looking at this document of Cami. The nice thing about Cami is that I can write on the document rather than on the skills, rather than on the screen. So let's get rid of you. So the question is something derived about accretion disks. So I'm going to have to remind myself how an accretion disk works. Accretion disks are one of the most important applications of the Navier-Stokes equation in astrophysics. Let's remind ourselves what the Navier-Stokes equation looks like. That was it just there, but so it's basically adding this viscosity term. I think here, yeah, here's a good full version of it. I will stick this on screen. So Navier-Stokes equation. The u dt plus u dot grad u is 1 over rho grad P. I've been reliably informed by my students that I wrote grad P wrong, and they're all correct, which is probably true. Won't really matter here, but let's keep in the potential term that's lacking from here, and then we have the viscosity term, grad squared U plus a third del of the divergence of U. So, accretion disks are one of the most important applications of the Navier-Stokes equation in astrophysics. By the way, these lecture notes I'm looking at, I think, are freely available online if anyone wants to go and look at them. They are written by Chris Reynolds, who is a professor at Cambridge, part of the Part 2 astrophysics course, and I hope I won't get in trouble for giving them out for free. They are truly freely available online, and maybe not supposed to draw attention to that, but I don't think Chris would mind. So consider some gas flowing towards some central object, star, planet, black hole. So let's draw this as we go. Let's keep on updating. In fact, let's have this over here. Left-hand side is EpicPen. We've got some central object. Let's make it a star. So here's our star. And gas from somewhere is wanting to flow towards it. And that gas will probably have just a little bit of net angular momentum. So I could draw all of it as coming in like this. It's not that actually all of it's coming in with some velocity like this. It's actually that it's coming in at velocities in all directions. But if you take a box like this and you ask, like, okay, what's the net flow? The net flow of that box will just tend to have some small component. Actually way smaller than the individual components, but it will still have some. This is just kind of a good law of nature, is that there has to be a really good reason for anything to ever be zero, and there's no really good reason for the angular momentum to be zero, ergo it is not. That might seem like a kind of backwards physical relation, but actually that works really well. So it's coming in and it has some little bit of angular momentum, and we're only going to draw the ones which are coming in, and it settles into a plane specified by the mean angular momentum, so it settles into some disk. Gas flowing in at the edge of this disk. No, I don't think there's a redo on this, annoyingly. This is an ugly disk. So that material is settling down onto this disk. Right hand rule, so actually it should be going the other direction. So the disk is spinning like this, and so it has some net angular momentum vector heading up here. Do better on that line. In fact, let's get the gas blue. So the gas is spinning like this. Blue gas, that makes sense, right? Oh, oxygen's blue. In the vertical direction, parallel to the angular momentum, the system will come into hydrostatic equilibrium with internal vertical pressure. So that's basically saying if we zoomed in on a bit of the disk, it wouldn't actually look completely flat. It would look like something like this, where there's a lot of pressure at the center and then less at the outside, and the whole thing's in equilibrium. We won't worry about the vertical direction. So here, this would be the vertical direction, this would be the radial direction. We won't really care about that. Honestly, I don't think that there's much that you haven't learned, that you've learned in your... I don't think there's much in like high-level astrophysics that you haven't learned by year 11. It's just applying and applying and applying to those applyings. The right-hand rule is a good rule. It's kind of annoying because it's completely a convention. Like, you just had to choose, do I use my right hand or do I use my left hand? But as long as everything in physics uses the same convention, that convention becomes kind of meaningful. In the radial direction, the system will achieve a state where the centripetal force is supplied by gravity and the radial pressure gradient. So if instead of zooming in on a vertical slice, we zoomed in on some radial slice, so that we had outwards is the radial direction, this is the angular direction. We expect the forces to roughly balance, because stuff, like in equilibrium, stuff isn't moving one way or the other. So that outward force is caused by a pressure gradient. Again, there's lots of gas here, less gas here, less gas still here. And that inward force is caused by gravity because, again, still there is at the centre this system. The star. We can do a better phi than that. Is that the right direction? R theta. No wait. R theta. Z. Yep. This is a different plot, so it should have some kind of delineating line. So this is the special case where the disk is thin. Meaning the scale height in the vertical direction is much less than the radius r, then the radial pressure gradients are negligible, and basically this is angular momentum supported. Oh, this is what I want. Here. Support. Almost. No! Why would you do that? And momentum. Support. Where omega is the angular velocity which means that to set this up, we need different. I'm now scared to use that undo button. Different angular velocity with radius. So that means that our disk has a different speed here, here, and here. That's a really ugly drawing. If I add more lines, it'll make it prettier. Oh, actually turned out to not really be true, shockingly. So this means that fluid is moving past each other. If we actually look at this, the further you go out, the smaller the angular velocity. So fluid at the very outer edge is dawdling along, and fluid further in is moving faster and faster, and fastest at the center. That sort of makes sense intuitively. Like if you think of something like water swirling down a plug hole, or equally a whirlpool in the ocean, that's exactly what we expect, that it's kind of a gentle effect far out, and it gets faster and faster as you go further in. Oh, I can select these things and change the color and move them. Interesting. So, things don't like to have different angular momentum. So they'll tend to try and equilibrate, and because things on the inside have less angular momentum? No, that's not making much sense. I've got to think through if that's a good intuitive explanation. Things don't like to have different energies, so actually the better question is always like, what does it look like as a system approaches virialization? What does it look like as a system approaches its kinetic and its potential energy being comparable? I think this is actually quite hard to picture. This is how it's always talked about, that like a small amount of the mass takes a large amount of the angular momentum out to large radius. I'm not going to fight with it here, but there are other ways to conceptualize this. But that is the kind of effect you get, basically. Like there's a nice experiment you can do where you start with some mass like this, and then you let it do this effect, and it goes like this over time until it gets to the center. And so most mass is moving out, is moving in, a little bit's moving out, but at the same time, for it to collapse, most angular momentum is moving out and a little bit's moving in. So it's kind of the trade-off between those two forces. So let's set up a model for it. Go So we're going to assume geometrically thin, cylindrically symmetric, axisymmetric, hydrostatic equilibrium in z direction, so we can ignore z motion. We basically have Keplerian velocity, so this is saying that even though the energy transfer is coming from viscosity, it's not changing the velocities very much, it's just an energy sink. So something unwritten here, but I think worth saying, this is also assuming that the radial velocity is much less than the tangential velocity, because otherwise we wouldn't have this case. The bulk viscosity is 0. I can't even remember what bulk viscosity is, but that's probably fine. So the continuity equation, that's just mass flow. We get it's axisymmetric, so nothing should vary with the angle. There's no vertical velocity, so we've just got this left. Fine. Now we can define the surface density and integrate throughout. We can integrate throughout because that integral is in z, nothing depends on z, and we get this kind of nicer expression. Let's put this to one side as well. That d by dt of the surface density plus 1 over r d by dr r surface velocity ur equals 0, which is just mass conservation. We can get the same result by thinking of the disk as a set of annuli. So it's just an equivalent result, but it's always nice to hear equivalent results. Rate of change of mass in the annulus equals flux into the annulus minus flux out of the annulus. So the mass in the annulus is equal to this, because this is the area of it, 2 pi r delta r. This is the thing with delta r times the surface density, so that gives mass. Is the flux into the annulus, which is the rate that stuff's flowing in through this boundary, actually flowing out because UR is generally negative. I should go back actually to this. What I've written here isn't necessarily true. I actually want to say this, I think. I only want to make comments about their magnitude, not their direction. Because I can't think of a case, unless you go to like a fancy geometry, where UR is not less than 0. Maybe at the edge of the disk. Put it in general. Just in case that's wrong at some point. And then this is the rate of flow through the top boundary, where we're just putting in a delta r. We're going to get rid of everything that is delta r squared eventually. Oh no, we don't even need to do that. This actually comes out perfectly as when we divide through by the delta r, which doesn't depend on t. The only thing that depends on t is this, divide through by the 2 pi. This is, from first principles, a derivative. Cool. So that's just exactly the same result as we've got written up here, just deriving it in a different way. Let's start by using our trig/calculus result. No, our ring/annulus result. fun thing about handwritten notes is you can completely go off on a tangent if you can't read them well. And in general, you can't. Can I? Yeah. So the rate of change of angular momentum is the angular momentum of mass entering the ring minus the angular momentum of mass leaving the ring plus the net torque on the ring. So angular momentum is density times r squared omega. Oh, the mass times r squared omega, mr squared omega is the angular momentum. This is entering ring, this is leaving ring. Again, actually the signs are different, so this probably should be the other way around. No, I think here actually this will tend to be greater than 0. Signs don't matter as long as we are pretty cautious about using them consistently. And this is the torques, and the net torque is going to be the torque on either side, where Fr is 2 pi r sigma ur. Yes, because this is the rate of flow of angular momentum through this side. Let me just really make sure that I understand that. 2 pi r ur is the rate of flow of mass over this. So it's just the rate of flow of mass over 2 pi r ur epsilon. Rate of flow of mass over times the angular momentum. So this is the equation in question, and actually it's referred to none of the things we've looked at so far. So that leaves me a little bit stumped in that I have done nothing to help channel me to a solution. I just relearned some physics. Woe is me. GR is the torque exerted on the disk of outside R by the inner radius of R. So I think we'll get at it by let's just grab an article for torque, make sure we've got it right. Torque, tau, or in our case G, so let's call it G. G is R cross F. So why is this equal? I'm going to go back quickly through the notes and just see if this is derived anywhere. So we're just looking for a big G. That's vorticity. And now we're back in instabilities. So no, it really has come from nowhere, and it's very fair of my student to have been like, where does this come from? At least it's come from nowhere that I can see easily. And I think we might need to So let's take the Navier-Stokes again. We've got this term will still be talk. dt by du is is effectively the force. Do we care about pressure gradients? We do not. Do we care about gravitational gradients? We do. We're changing where we are in gravity, so it's going to be gm over r squared in the r direction. This is just sigma squared, and then we've got plus grad squared u. What's a third? Grad of grad dot u. Now u is almost entirely the tangential velocity. So u is roughly speaking no, that's wrong. Omega r in the phi direction. So this is 0 because the divergence of this is 0, I think. Grad squared u, I always forget how to calculate grad squared. That is also omega squared, so let's put it in those terms. Truly just omega squared? I think so. Is the viscosity dimensionless? I'm pretty sure, pretty certain that the Reynolds number is not Reynolds of the person who wrote these notes, but you never know. Okay, so we've already had Navier-Stokes introduced there. This is where eta is introduced. Kinematic viscosity. Eta is independent of density. Just assume it's all fine. That's my idea. Ooh, no, we want, we're still getting this equation. But wait, but omega is a function of r, right? Yeah. So let's get this entirely in terms of r. Omega r is gm. That's omega squared over r. No, is it? That's r omega squared. Root GM R? No, wait. Root GM r to the minus 3 over 2 times r to the minus half, root GM over r. So this might take me all the way to my meeting, working this out. So actually in full, this is maybe the better way to put it, u is ur in the r direction. It's gm over r in the phi direction. Where u r is much less than. Let's do it in the square version because then we actually have less to write. U r squared is much less than gm over r. This is the kind of thing that sometimes I show to my students and they're like, oh, this is how you can get this in one line. And I'm like, I've got to pretend like I knew that. It's a bad habit, pretending that you knew stuff that your students worked out. It's much better to be like, oh, wow, that's great. Thank you for working that out for me. I do a mixture. So let's get back to the equation that we're trying to get to. It's nice to work the problem from both ends, to kind of both be like, okay, from first principles, this is what we should have, and also this is where we want to go, so let's go that way as well. So the good news is this term actually doesn't matter because we're going to be taking the cross product. Any term proportional to r also doesn't matter because we're going to be taking the cross product. So it's just the terms in the phi direction. The derivative of ur isn't going to appear in here because it's just small. And there's no phi component of this, so that truly is 0. So we have I've got to remind myself what the Laplacian of a vector looks like. Cool, I can express it like this. So if I put it like that, run out of space. Laplacian of A is the gradient of the divergence minus the curl of the curl. Maybe some people have these things stored in their head. I have to look them up every time. So again, the gradient of A is 0, so it's just this one. or the gradient of u is 0. So it's just the force is mu times it's minus mu curl of gm over r in the phi direction. So, which is also equal to curl of r phi. No, I want to keep all the r's in. Because what are we going to get? We're going to get the, it's only the d by dr term that's going to be meaningful, and that's only going to come out in the z direction. So that's going to be curl of z direction minus a half now we just get, no, we truly just get back to this. So that's going to give us in the curl of the z direction, where we're going to get a term. It's again only going to be the radial derivative, so it's going to be plus that minus a half d omega by dr. Wait, negative times negative. So let's write this more simply. $10 says that I've got a sign error somewhere in here. But then another $10 says that they cancel out. And then that's in the theta direction. So we now have a force, and the torque is, this is actually wrong, this is the mass times this. Or somewhere I've lost, oh no, I've lost the mass here. This is the acceleration, not the mass. Which means that the force is this times the mass. Am I going to write this out? Yeah. So is the mass of this element how do we not have a delta R in here? How have I got away without that? Also, this factor of 2 doesn't look like it's going to disappear. I thought I was almost there, and now I got stuck. Because how do I go from this acceleration to a force? Multiply through by a mass, but how would that not bring out a delta R? When I learned this for the first time, I remember getting stuck on a bunch of these. So we've just kept this one. That one goes to 0 unless you keep the UR in. So any reason we want to keep the UR in, I really don't. God damn it, maths. / physics, why wouldn't you just work yourself out? This formula for torque might be oversimplistic here. Come on, brain, think. So this formula for torque kind of assumes that the thing is not moving radially. Which is untrue here, but that radial motion is a small component of it. I'm stuck. And I have to go to this meeting in 10 minutes. Just gonna check the email from the students, see if they got any further in any ways that I haven't. No. This person will be giving a talk this week. I could ask them then. That's an insane way to do it. Still, that's cool news. Annoyingly, I didn't bring any of my textbooks home when the lockdown started. Because I have a feeling it might be in there. I think I'm going to end the stream here on this completely stumped place and then use my last few minutes before this meeting to go and look at the textbook. So thanks for joining me. Sorry I didn't work it out. Not that I think that that's why. I don't think people are here being like, yeah, I'm really going to get to the answer of this physics question. See you later.